Welcome to the 11th video on compressible fluid flow. I am Rajagiri, Assistant Professor from the Department of Mechanical Engineering, Rajagiri School of Engineering and Technology. In this video, we will discuss about nozzles and diffusers. Before we start discussing about nozzles and diffuser, first we have to understand how the change in area affects a compressible flow. For this, we will obtain a relation for change in area in terms of Mach number. For this, consider a variable area duct as shown in figure. Within the duct, we will consider an elemental volume which is marked by the dashed lines which represents our control surface. As the fluid passes through the control volume, it experiences certain changes in its values. The change in values are represented by incremental terms. Now, using the law of conservation of mass and law of conservation of energy along with the reduced form of previous equation for an isentropic flow, we can obtain the following relations connecting the change in area with Mach number. The first equation represents the change in area with respect to Mach number, and the property of fluid that is under consideration is change in pressure along with Mach number. In the second equation, we see that the equation represents change in area and is expressed in terms of Mach number as well as change in fluid velocity. The third term expresses change in area in terms of Mach number as well as the change in fluid density. Using these three equations, we can understand how a compressible flow gets affected when there is change in area and how the properties like pressure, fluid velocity, density varies as the flow passes through the variable area duct. Now let's see what is a nozzle and a diffuser. A nozzle is a device employed in a flow passage to gain velocity at the expense of pressure. That is, a nozzle reduces the pressure energy which is involved in the term of enthalpy and increases the kinetic energy of the fluid. As the fluid passes through a nozzle, its pressure reduces and velocity increases. So basically a fluid expands as it passes through a nozzle. This is known as nozzle action. A diffuser is a device employed in a flow passage to increase the pressure at the expense of velocity. Here, as the fluid passes through the diffuser, its pressure increases and velocity decreases. That is, the fluid gets compressed as it passes through the diffuser. This is known as diffuser action. Some points to keep in mind to understand how a variable area duct behaves as a nozzle or as a diffuser. For a converging duct, as the flow progresses, it experiences a reducing area. That means the change in area in the direction of flow will be negative. For a diverging duct, as the flow progresses, it experiences an increase in area. That is, as the flow progresses, dA value will be positive. For a diffuser, as the fluid passes through a diffuser, it undergoes compression. Pressure increases at the expense of velocity. So in the direction of flow, the change in pressure is positive, that is dP is positive. For a nozzle, the fluid passing through a nozzle undergoes expansion. The velocity increases at the expense of pressure. Here, the pressure reduces in the direction of flow. Hence, change in pressure, that is dP, will be negative. Now let us see how a converging duct acts as a nozzle or as a diffuser. Consider a subsonic flow passing through a converging duct. As the flow progresses, it experiences reducing cross-section area. That means dA is negative for a converging duct. For a subsonic flow, the term 1 minus m square yields a positive value, whereas the term m square minus 1 yields a negative value. Therefore, from the equation, we can conclude that for a subsonic flow passing through a converging duct, the pressure decreases, that is dP is negative, fluid velocity increases, that is dC is positive, and fluid density decreases, that is d rho is negative. Hence, for a subsonic flow passing through a converging duct acts as a nozzle. Now consider a supersonic flow passing through a converging duct. For a supersonic flow, 1 minus m square is negative. M square minus 1 is going to yield a positive value. The duct is a converging duct, so dA value is negative. So we can conclude that when a supersonic flow passes through a converging duct, the pressure increases, that is dP is positive, velocity decreases, that is dC is negative, and density increases, that is d rho is positive. Hence, for a supersonic flow passing through a converging duct, the converging duct acts as a diffuser. Now let's see the case for a diverging duct. Consider a subsonic flow entering a diverging duct. As the flow progresses, it experiences increasing cross-section area, that is dA value is positive. For a subsonic flow, the term 1 minus m square yields a positive value and the term m square minus 1 yields a negative value. So from the equations, we can conclude that for a subsonic flow passing through a diverging duct, the pressure increases, that is dP is positive, velocity reduces, that is dC is negative, and density increases, that is d rho is positive. Hence, for a subsonic flow passing through a diverging duct, the diverging duct acts as a diffuser. Now consider a supersonic flow passing through a diverging duct. For a supersonic flow, the term 1 minus m square yields a negative value. The term m square minus 1 yields a positive value. Since it is a diverging duct, the dA value is positive. So we can conclude that for a supersonic flow, when passing through a diverging duct, there will be reduction in pressure, that is Pp will be negative, reduction in density, that is d rho will be negative, and an increase in velocity, that is dc will be positive. Hence, we can say that for a supersonic flow passing through a diverging duct, the diverging duct acts as a nozzle. Now let us see how a CD duct can act as a nozzle or as a diffuser. The CD duct is a combination of a converging duct and diverging duct. For the CD duct to act as nozzle, there should be continuous drop in pressure as the flow progresses through the CD duct. To attain this, we should have subsonic flow in the converging duct so that it will act as a nozzle, and there should be supersonic flow in the diverging duct so that the diverging duct will act as a nozzle. If you are able to attain this, then the CD duct will act as a nozzle with continuous pressure drop. So when a subsonic flow enters into a CD duct, as it passes through the duct, it accelerates with reduction in pressure, and it should accelerate such that at the throat of the CD duct, that is at the end of the converging part, it should attain a Mach number equal to unity. After that, it enters into a diverging duct where it will act as a nozzle and further accelerate the flow from Mach number equal to 1 to supersonic flow regimes. Hence, a CD duct will act as a nozzle if we have inlet condition as subsonic and the throat condition equal to sonic conditions. We can use a CD duct to accelerate a subsonic flow to a supersonic flow. It is important that the condition at the throat of the CD duct be equal to unity, because if it is less than unity, then what we have is a subsonic flow entering into a diverging duct. The diverging duct will act as a diffuser and decelerate a flow. In that case, a CD duct acts like a venturi. So, the CD duct having unity Mach number at the throat with subsonic inlet condition can act as a nozzle. Now let us take the case of a CD duct acting as a diffuser. For the CD duct to act as a diffuser, the converging duct should have supersonic flow and the diverging duct should have subsonic flow. That is, at the inlet of the CD duct, the flow should be supersonic, and as it passes through the duct, there should be increase in pressure, and eventually the velocity reduces and the Mach number should become equal to 1 at the throat. This flow, when passing on to the diverging duct will act as a diffuser and further decelerate the flow, resulting in a continuous increase in pressure, and the entire CD duct will act as a diffuser. So, a supersonic flow can be decelerated to a subsonic flow isentropically, that is without any energy loss, available energy loss, using a CD duct, provided we have a supersonic flow condition at the inlet and at the throat Mach number is equal to unity. A converging duct with subsonic flow when acts as a nozzle is referred to as a subsonic nozzle. A diverging duct with subsonic flow when acts as a diffuser is referred to as a subsonic diffuser. A CD duct with subsonic flow at the inlet and supersonic flow at the exit when acts as a nozzle is referred to as a supersonic nozzle. In the same manner, a converging duct with supersonic flow when acts as a diffuser is referred to as a supersonic diffuser. A diverging duct with supersonic flow when acts as a nozzle is referred to as a supersonic nozzle. A CD duct with supersonic flow at the inlet and subsonic flow at the exit is referred to as a supersonic diffuser. Now we see that the diverging duct with supersonic flow is referred to as a supersonic nozzle, and a CD duct with subsonic flow at the inlet and supersonic flow at the exit is referred to as a supersonic nozzle. The difference being, in the diverging duct the flow is entirely supersonic, whereas in the CD duct the flow is initially subsonic, which is accelerated to supersonic condition. The same is applicable for supersonic diffusers. In a CD duct which acts as a supersonic diffuser, the inlet condition is supersonic, whereas the exit condition is subsonic. Whereas for a converging duct acting as a supersonic diffuser, the flow is supersonic throughout the duct. While discussing about CD duct acting as nozzle or diffuser, it was mentioned that the condition at the throat should be sonic condition, that is, Mach number should be equal to 1 at the throat. Now consider the CD duct acting as a nozzle. Let's suppose that at the throat Mach number is equal to 1. Now this is a critical condition. On one side we have a subsonic flow, on the other side we have a supersonic flow. So the flow is entering the diverging duct at critical condition. Now whether it moves as a subsonic flow or has a supersonic flow depends on the conditions prevailing at the exit of the diverging duct. So apart from the condition that Mach number should be equal to 1 at the throat, there has to be other conditions which has to be met for the diverging duct of the CD duct to act as a nozzle. We will discuss these points in the upcoming slide when we deal with how a CD duct behaves towards varying back pressure.